Hey guys, welcome back to Pop 'em Up Chem. Today we're doing the second episode of our Unit 7 and 17 series, and it's on Le Chatelier's principle. Can I just remind you, comment below, like, subscribe, hit the bell icon, and share this video, this channel, and our two other channels, Pop 'em Up Life and Pop 'em Up Food as well. In the description, you're going to find timestamps for this video and links to the other channels and other content. Let's get on with it. So the plan for this lesson is to understand the impact of Le Chatelier's principle. We're also going to try and apply that principle to explain how changes affect an equilibrium, and we're going to look at an industrial equilibria and the catalyst used in it. Let's not forget our refresh though. So I want you to write the Kc expression for the complete combustion of methane. That's CH4. Pause the video to give yourself a little bit of time to do that. So with a question like this, I'm always going to need my balanced equation before I can do anything else. So CH4 plus O2 is always going to equal, of course, CO2 plus H2O. Going to balance that up, and I'm going to need a 2 in front of my H2O to balance my hydrogens, and then I'm also going to need a 2 in front of my O2 to balance my oxygens. Remember, Kc is going to be our concentration of our products divided by our concentration of our reactants. So our products being CO2 and H2O, and remember to give it H2O to the power 2 all over CH4 times O2 again squared. Okay, so what is Le Chatelier's principle? Well, Le Chatalier was some French dude about turn of the last century or just before. He was a chemist deeply ingrained in industry, and he found that, as this statement shows, a system at equilibrium responds to disturbances in such a way as to minimize the disturbance. What does he mean? Well, really, he's saying that any system at equilibrium will oppose what you do to it. If you increase the concentration, it will try to decrease it. If you increase pressure, it will decrease it. Temperature, volume, all the same. The equilibrium will resist you. Let's break these factors down one by one. First, concentration. Let's just get it out of the way. Equilibrium constant is not affected by changes in concentration. That's really, really important. At a constant temperature, products over reactants will equals Kc. And if we change the concentration, although initially it may seem as though Kc is going to change, at a constant temperature, Kc remains the same. And instead, the overall concentration of the reactants or products is going to change to keep Kc the same. Instead, we can see changing the concentration more like shifting it towards being a value of Q. We did Q last lesson. It would be the reaction quotient while the reaction shifts back towards giving us the same value of Kc, because at the same temperature, it will be the same. So what does this really mean? Well, decreasing the reactant or increasing the product will shift the equilibrium to the left. Well, that's kind of hard to visualize. So let's just think. We've got reactants on the left-hand side and we've got products on the right-hand side. And we know that Kc is equal products over reactants. Now, at a particular temperature, so we're not changing the temperature here once again, we know that Kc will remain the same. So if we decrease the concentration of a reactant, let's say, that is going to decrease the value in the denominator up here. And that means that the reaction is going to shift to bring that value back up. So some of the products are going to move and change back into some reactants to balance that out. So the proportion of those together will still equals the same value of Kc. This is what we call the shifting of the equilibrium. Remember, that is just Le Chatelier's principle. It's resisting the change. The same is true if we increase the concentration of our reactant. Now, if we increase the concentration of our reactant, then the denominator of the fraction is going to increase, and therefore some of the reactants will turn into products in order to keep that proportion the same, in order to keep Kc the same. So Le Chatelier's principle is staying true because the value of Kc must remain the same, and so therefore the concentration shifts in order to keep the proportions the same. So let's have a little look at an example. I'm just going to choose some random numbers for this so we can plug them in. So let's just say we've got a concentration of 2, 1, 8, and 1 will work. Now, if we do our calculation there, we're going to get 8 times 1 divided by 2 times 1 equals 4. Fantastic. Okay, which is our Kc. Now, if we change the concentration, then let's have a look at what happens. So I'm going to change the concentration of the carboxylic acid. I'm going to increase the concentration. So we're going to do 8 times 1, and then I'm going to make it 2. So now we've got 8 divided by 4, which of course gives us an overall value of 2. The more observant among you will notice that 2 is not equal to 4. So what's going on here? Well, now Le Chatelier's principle comes into play. These have to maintain the same value. So the concentration of our reactants is going to shift to give more of the products, because we need a 4-to-1 ratio, and at the moment it's a 2-to-1 ratio. So we can begin to start generalizing these changes that occur when we change something. So increasing the alcohol or carboxylic acid will make the bottom line larger, and so Kc will be smaller. And so therefore, if Kc has become smaller, that is going to increase the amount of products formed to balance that out. And of course, the inverse is true if we do the same with any of the products. So summarizing in full, we can write a table a little bit like this, which tells us whether the equilibrium will move to the right or to the left. I don't recommend remembering this kind of table. I recommend using Le Chatelier's principle in every question that you're given, and it will give you a better understanding of what's being asked of you. Time to try your hand at some questions then. So our first question is asking us, how would increasing the concentration of hydrogen gas affect the position of this equilibrium? Pause the video here to give yourself some time. Pop them up. Now, in this reaction, H2 is a product. My mistake, it's not a product here, it's on the right-hand side. So if we write Kc is going to be our products over our reactants, that's CO times H2 divided by H2O, and C we don't include because it is a solid, so it doesn't have a concentration. Now, if H2 is increased, that means we're going to increase the overall top of the fraction, and that means that it's going to shift towards the left-hand side or to the bottom of the fraction, so that the H2O is increased. Okay, next question then. How would decreasing the concentration of NH3 affect this equilibrium? Pause the video to give yourself some time. Pop them up. So with this one, we are decreasing the concentration of NH3. It's going to be NH3 times HCl over NH4Cl. Now we're suggesting decreasing one of the products which is on top of the reaction, and so therefore if we decrease that, the reactants are going to shift to replace that. Remember, always remember Le Chatelier's principle. It's going to shift to balance out for Kc. Hopefully you're getting faster then. Next question, similar. How would decreasing the concentration of I2 affect this reaction? Pause it here to give yourself that time. Pop them up then. So in this one, I2 is a reactant. So we write our expression for Kc, and now we're decreasing the denominator. So the products are going to shift to replace and rebalance the ratio. And so the reaction will shift to the left-hand side. Now we've got an understanding of concentration, we can begin to have a look at pressure. Now, unsurprisingly, when we consider pressure, we're going to look only at the number of molecules of gas. And also remember Avogadro's law from our stoichiometry that 1 mole of a gas will always occupy the same volume. So when we think about what pressure is, we think about the molecules bumping up against the side of their container. So if there is an imbalance in the number of molecules of gas in an equation, maybe 2 moles on one side of an equation, an equilibrium, and 1 mole on the other side, one of these sides, if it was taken to completion, would have a higher pressure. In this case, the reactants A plus B has 2 moles of gas compared to only 1 mole of gas. That means that the reactants here exert a higher pressure. So what would happen if we were to increase pressure from the outside? Well, as always, the equilibrium will resist us and it will shift to the side of the reaction that has a lower pressure and produce more of C in this case. Now, the reason being because of Le Chatelier's principle. It is resisting the change. We increase the pressure, so the reaction is moving towards the side that decreases the pressure. So by the same logic, if we decrease the pressure, the reaction will shift to the high pressure side, in this case, A and B. And of course, if there was the same number of molecules on both sides, we would have no overall change because both sides of the reaction would have equal pressure. To summarize, the equilibrium constant is not affected by changing in pressure. Just like concentration, only the temperature can affect the equilibrium constant. Increasing pressure is always going to move the reaction to the side with the fewest gas molecules, and decreasing the opposite. The reaction at the bottom, we've got 4 moles of gas on one side, 2 moles of gas on the other. So we can kind of label those high and low. High with the 4, low with the 2 moles. So what would happen if we were to increase pressure? Of course, it would move to the right-hand side because that's the low pressure side. And as we increase the pressure, the equilibrium will resist that change and move to the right. If we decrease the temperature, we'd get the exact opposite because the equilibrium would shift to the high side. Again, we can summarize this with increasing pressure, moving to the side with fewer gaseous molecules, and decreasing pressure moves to the side with more gaseous molecules. Okay, let's try some questions on pressure then. First question, how would decreasing the pressure affect the above equilibrium? Pause the video now, give yourself a bit of time. Pop them up with a pressure question. First things first, we want to count how many moles of gas there are on each side. So we've got 1 for the reactants and 2 for the products. So there are more moles of gas in the products, and it's asking us how decreasing the pressure would affect the equilibrium. Well, if we decrease the pressure, the reaction will do the exact opposite. So I'm just going to label the side with more moles the high pressure side, and the reactants as the low pressure side. We're decreasing the pressure. The reaction will therefore shift to the right hand side to increase the pressure. Okay, next question. Similar kind of question. How would increasing the pressure affect this equilibrium? Pause the video now to give yourself the time. Okay, pop them up. I'm going to do the same thing that I did last time. I've got 1 mole of gas on my reactants, 2 moles of gas on my products. So I've got a 1 to 2. That means that I've got the low pressure reactants and the high pressure products. I'm trying to increase it. The reaction is trying to do the opposite. And so therefore we're going to shift the reaction to the left-hand side. Okay, last question on pressure. I want everyone to get this right. Try this one. How would decreasing the pressure affect this equilibrium? Pause the video now to give yourself the time. All right, pop them up. Hopefully by this point, you see that we always need to know the number of moles of gas when we're dealing with pressure. So in this one, we have a 2-to-2 reaction. So we have 2 moles of gas on one side, 2 moles of gas on the other side. Now, that means there's neither a high nor a low pressure side. And so if we decrease the pressure, it's going to have no effect on the position of the equilibrium. Turning our attention to temperature, we have slightly different thing to look at because temperature can affect the value of the equilibrium constant. And so we really have to focus on whether a reaction is exothermic or endothermic. And so whether it's got a positive or negative enthalpy change. So for this reaction, we can see that going from left to right is an exothermic reaction. So if we have an exothermic reaction, then as we increase the temperature, we're going to lower the Kc. What does that really mean? Well, if we have a look at our equilibrium constant and also understand the thermodynamics, we start to build the picture. So for this reaction, the reaction going from left to right is exothermic. That means it gives out heat. And of course, conversely, the reaction from right to left is endothermic and so takes in heat. So when we think about the Chatalier's principle, if we increase the temperature, the reaction wants to decrease the temperature. So it will shift in the endothermic direction, and so therefore increasing the reactants for this reaction anyway at a higher temperature, because the reaction is going to go in the endothermic to reduce the temperature. So overall, how can we describe temperature's effect on equilibria? Altering the temperature affects the rate of both the forward and backward reaction. However, it affects these at different extents. And this means that the equilibrium actually moves and we actually get a new equilibrium constant. And the direction of that movement depends on the sign of the enthalpy change. To try and help you visualize this, let's think about an exothermic reaction giving out heat to the surroundings. So as heat is given out to the surroundings, if we increase the temperature, then it becomes more difficult for the reaction to offload the extra heat. If you like, you could imagine it as constrained. Whereas with an endothermic reaction, endothermic reactions require heat going into the reaction, and because of that, as we increase temperature, it actually increases the reaction's ability to take in energy. Conversely, if we lower the temperature, the reaction trying to give out energy, the exothermic reaction, finds it easier to offload this energy to its cooler surroundings, whereas the endothermic reaction can take in energy less effectively because there's less extra energy surrounding the reaction. To summarize that then, temperature is a little bit more nuanced, as we have to know whether the reaction is exothermic or endothermic to know how changing the temperature will affect the position of equilibrium. Let's try some questions on temperature then. First question, how would decreasing the temperature affect the position of this equilibrium, which is endothermic going to the right hand side, the forward reaction? Pause the video to give yourself the time for that then. Pop them up. Now in this reaction, we can see that there's a positive enthalpy change for the forward reaction, and that means we know that the reaction is endothermic in the forward direction. And if we know it's endothermic in one direction, we then know it is exothermic or have a negative enthalpy change in the other direction. So how would decreasing the temperature affect the position of the equilibrium? Well, we know if we decrease the temperature, we're going to get the reaction to resist us, and it's going to try and increase the temperature. Well, how can a reaction do that? using Le Chatelier's principle, it's going to shift to the left-hand side to be able to give out more energy to the surroundings. What's this going to do to our value of Kc? Well, Kc, as we know, is our products over our reactants. We've just said that it's going to shift to the left-hand side, so it's shifting to the bottom of the fraction, which means we're going to have a larger denominator, which means overall we're going to have a smaller value for our Kc. Okay, have a shot at this one then, guys. How would increasing temperature affect this equilibrium? Pause the video now to give yourself a bit of time to work it out. Pop them up. Okay, with this reaction, we can see that the forward reaction is exothermic and therefore the backwards reaction is endothermic. So if we're increasing the temperature, remember, using Le Chatelier's principle, it is going to shift to the left-hand side because the reaction is going to try and decrease temperature. If we have a look at our effect on Kc, write out our expression for Kc, and we can see a shift to the left-hand side is going to increase the denominator, which that means we're going to decrease the overall value of Kc. Okay guys, last question on temperature. Have a go at this one. How would decreasing the temperature affect this? Remember to pause the video to give yourself the time. Pop them up. Okay, with this one, we can see that it's exothermic in the forward reaction and endothermic in the backwards reaction. Now, of course, we're decreasing the temperature, so the reaction's going to fight that. So the reaction's going to go towards its exothermic direction. And because of that, it's going to shift to the right-hand side. Let's have a quick peek at what that does to Kc. Now, Kc, products over reactants, remember. Now, if we've got a shift to the right-hand side, we're shifting towards our products. So we're going to increase the value of our numerator. Increasing the value of our numerator is going to overall increase the value of Kc. So I want to try and link the idea of our rate unit with this unit and think about what it means to shift the equilibria and rate. So rate and extent are not the same thing. Let's have a look at an example of what the ideal conditions for this reaction to produce ammonia might be. To illustrate, we've got 4 moles of gas on the left-hand side, 2 moles of gas on the right-hand side, and the forward reaction is exothermic. So that would indicate to us ideal conditions would be low temperature because the reaction would try and fight us, and high pressure, again, because the reaction would move to the low pressure if we're trying to produce ammonia. However, in industry, we use these conditions, 450 degrees and 200 atmospheres. So why? That doesn't seem that cold to me. And also 200 atmospheres isn't nearly as high as we could push it. I mean, it's more than I could handle, but it's not particularly high. So why do these not line up? Now, the reason is an increase in temperature speeds up the rate of the chemical reaction and can have a desired effect on the rate as opposed to the extent. So we get if we get 100% yield or 99% yield at 1 Kelvin, let's say, just a stupid example, and it takes us a year to get there, then what's the point? We need to make less yield potentially in a lot less time, or a lot faster, so we can get to the equilibrium quicker. And we can also help ourselves along in this process by using catalysts in industrial processes. So catalysts are really, really useful because although they may not move and they do not shift the position of equilibrium because they lower the activation energy of the reaction in both directions. So if you think about your reaction pathway diagram, the catalyst lowers that overall peak for the exothermic reaction and lowers that activation energy, but also going back in the other direction. So we have an overall lowering of activation energy, which is fantastic. It doesn't move equilibrium, but it does mean we can reach equilibrium sooner under the same conditions, which can be just as useful in industry. I just want to reiterate that this does not affect the position of equilibrium, because it affects the backward reaction and the forward reaction to the same degree. However, this is useful for things like the Haber process, which we've already actually taken a little look at. That's the production of NH3 that we did earlier in the lesson, and we'll have a look at also later in the unit, but also other processes like the contact process. As usual, you're going to want to make sure you do some questions on this to make sure you understand how to apply these ideas. Thanks for joining me again, guys. Remember, comment below if you've got anything to say, want to give some feedback, like, subscribe, hit the bell icon, share the video, and check out our other channels as well. And remember, practice makes slightly better.